So I'm just going to read through this first part here. Just follow along with me as we go. If I mark things down, mark them down on your own paper. That way you can kind of have this as an example for what you do next. So why does moving railroad trays stay on the tracks? Most people assume that the wheel flanges keep the wheels from rolling off. But if you look at the flanges, you'll notice that they are rusty. They seldom touch the tracks except when they follow slots that the train from one set of tracks to another. How do the wheels on the train stay on the track? They stay on the track because their rims are slightly tapered, okay? This is important. They stay on the track. So I'm going to write reason off to the side. I'm also going to mark this down. They seldom touch the track because that's not something I expected. If you roll the tapered cup across the surface, it makes a curved path. So this is the tapered surface, okay? The wider part of the cup has a larger radius, rolls a greater distance per revolution, and there has a greater tangential speed than narrow part. So this is, the figure is explaining this. So I'm going to go ahead down here in the picture, and I'm just going to draw my tangential velocities. It said that the outer has a larger radius, therefore it has a larger tangential velocity. This one has a smaller radius, so it has a smaller tangential velocity. Okay, so this goes around a smaller circle, so it doesn't have to go as fast. This one goes over a larger circle. So it has to go faster. Okay. Makes sense? If you fasten a pair of cups together at their wide ends, simply taping them together and roll the pair along a pair of parallel tracks, the cups will remain on the track and center themselves whenever they roll off the center. Okay, so that's 8-4. Okay, so it's going to stay centered. And the reason being, if it rolls to one way, we get this kind of tapering effect. So if it rolls one way, the cup will roll in the opposite direction, sort of a thing. Okay, that's what I'm getting at least. This steers the pair towards the center. If the pair overshoots towards the right, the process repeats, this time towards the left as the wheel tends to center themselves. Likewise, for railroad trains, where passengers feel the train swaying on these tracks from side to side. Okay, that's kind of this here. So this is kind of this centering effect. Okay, this tapered shape is essential on the curves of railroad tracks. On any curve, the distance along the outer part is greater than the distance along the inner part. Okay, distance along outer greater than distance along the inner, as in figure 8.1a. Okay, so this is... Oh, that's a different one that's on here. Okay, so whenever a vehicle follows a curve, its outer wheels travel faster than its inner wheels. Okay, outer wheels faster than inner wheels. For an automobile, this is not a problem because the wheels are freewheeling and roll independently of each other. For a train, however, like the pair of fastened cups, pairs of wheels are firmly connected and rotate together. Opposite wheels have the same RPM, so rotations per minute at any time. But due to the slightly tapered rim of the wheel, its tangential speed along the track depends on whether it rides on the narrow part or the wide part. On the wide part, it travels faster. So when a train rounds a curve, wheels on the outer track ride on the wide part of the taper rims. Wheels on the narrow part, the opposite ones ride in the narrow part. In this way, the wheels have different tangential velocities, different tangential speeds, for the same rotational speed. This is R equals V equals R omega, so we talked about this equation briefly in action. Can you see that if the wheels were not tapered, scraping would occur and the wheels would squeal the whole way around? So I'm going to look at this one here. So the narrow part of the left wheel goes slower, so the curve goes left. Okay, so this here, this is the narrow part. This is slow. This is the wide part. This is going to be fast. Okay, so I'm assuming the tray is going to go away from me. If the train's going away from me, this is what I'm going to see. Here's the slow side. Here's the fast side. And it's going to be like this. It's going to curve. Okay? And then, at some point, it'll line back up and go straight. So the idea being, because it's tapered, because it's not the same the whole way, part of the wheel will go slow, part of the wheel will go fast, depending on where the track is on the wheels. Okay, so once I've read through it, I'm going to go to the other side. And now I'm going to answer the questions. But here's the key. You need to include one sentence from the reading per question to support your answer. So, number 2. Why would a tapered number 1. Why would a tapered cup roll in a circle if it rolled across the surface? Okay? Well, that was this picture here. So it said, because the wide part of the cup rolls faster than the narrow part, the cup rolls in a curve. That's almost literally what the question asked me. So I'm going to write that down exactly the way it is from the book. Okay, and I'm going to put a star here so that I know that this is the part that I wrote from the book. And it is, because the wide part of the cup rolls faster, then the narrow part, the cup rolls in a curve. And I don't need to do anything else for 1. That answered the question, and it was a sentence straight from the reading that helped support my answer. I just literally copied it down. That's perfectly fine. So now I'm going to go on to number 2. How are trains able to turn and stay on the track if they have no steering wheel and the flanges on the wheels are rarely used and cannot hold the train on the tracks? So this is that other stuff I was reading about. This idea that, okay, so when the narrow part's on the left, the wheel goes slower, so it curves left. Wide part's on the left, it goes faster, so it curves right. Okay? Along a track that curves to the left and the right wheel rides on the wide part and goes faster. Bottom wheel's on the left, it goes slower. Opposite is true when it curves right. Okay. There's a lot going on in this. To me, there's not one sentence that stands out, so I'm going to just kind of explain it first. So how does it stay on the track? Okay. Since the wheels are tapered, the speed of each wheel changes to balance the train's position. Okay, since the wheels are tapered, the speed of each wheel changes to balance the train's position. I'm going to say because their rotational velocity is the same. Okay, so since the wheels are tapered, the speed of each wheel changes to balance the train's position because their rotational velocity is the same. I need to have a sentence from the book that backs this up, so I'm going to look back through here. Tapered shape is essential, and then curve the distance. All right, I'm looking at here. Steers towards the fares, overshoots in time. Likewise, the railroad track appears to feel the train. Okay, this is kind of where it started talking about it here. If you fasten the pair of cups, they'll roll. they remain centered. This occurs because the pair to the left center, say the wide part, rides on the left track narrow part that seems to decay. And I'm just kind of skimming through here. I'm trying to find, okay, in what am I reading? What seems to be the key here? Okay, I'm going to use this one. In this way, the wheels had different tangential speeds for the same rotational speed. That'll explain to me why the train curves, because part of it is going faster than another. Even though they're the same wheels, they're rotating the same, they're not going the same speed. So that's what I'm going to write down. Again, you only need to write one sentence, but I do want one sentence from the reading. Here it is. In the same way, the wheels had different tangential speeds for the same rotational speed. Okay? And there we go. So the goal of this assignment is to get you to